Welcome to Calculus Asynchronous Learning. So, during this, we will go over, for this presentation, directional derivatives. It is suggested that you pause the recording from time to time to attempt the problems before I go through the solutions. If you have any questions, feel free to email me. Now, with that being said, let's get started. So, consider the function x cubed minus 12x. First of all, to calculate the tangent line at x equals 1, we take the derivative, plug in 1, that becomes the slope, then we use point slope form. That is given right there. So, derivative at 1 is negative 9. The value of the function at 1 is negative 11, found by plugging 1 into the function, which gives the tangent line y equals negative 9, x minus 1, minus 11. Now, we can also calculate the derivatives at negative 3, 0, and 2. And again, that is found just by plugging the x values into the function. Doing so gives f prime of 3, negative 3 is 15, f prime of 0 is negative 12, and f prime of 2 is equal to 0. Now, when considering the information this gives about the function, remember that not only is the derivative the slope of the tangent line, but also the derivative tells you whether the function is increasing, decreasing, or in transition. And so, for part C of the intro, that is what I'm looking for. So, now let's move on to the next item. Now let's move on to functions of more than one variable. So, recall from the past week, we've been dealing with functions similar to z equals x cubed minus y squared. Also recall that for these functions, it forms a surface. So again, instead of just being a curve that can be drawn on the plane, it represents a three-dimensional surface. Also recall this made calculating derivatives a bit more difficult because there's no single tangent line at a point. However, something we did early on was we inserted numerical values for one of the variables to give a result that's a curve. So, for example, if you take the trace for y equals 1, that results in the equation z equals x cubed minus 1, and it then gives the curve, which is a cubic. Also, if you take the trace for x equals 2, that gives the equation z equals 8 minus y squared, and it gives a curve that's an upside down parabola. Now, with each of these, we can calculate tangent lines. Although these tangent lines are, the first one would be the derivative of z in terms of x, and the second one would be the derivative of z in terms of y. So these are tangent lines parallel to the x-axis in the case of part A, and parallel to the y-axis in the case of part B. And for that reason, these are the partial derivatives of the function. A trace can be thought of in another way, which is to take a plane and to cut the surface either parallel to the x-axis or the y-axis. Doing so parallel to the x-axis allows us to calculate a partial derivative with respect to x, which appears as a tangent line shown in red on the figure below on the left. Similarly, taking a trace with y equals a number, or correction, taking a trace with x equals a number, results in a plane cutting the surface parallel to the y-axis and allows us to give the partial derivative of the function with respect to y as a tangent line. However, this limits us as we are left with only two directions which we can calculate tangent lines for. Any diagonal directions we are not able to calculate tangent lines for. As was stated in the beginning, I would suggest that you attempt this problem before listening to the recording. So at this point, look back at what you have for the notes for the previous slide. Attempt these parts of this problem. Pause the recording, and when you are done, listen to the remainder of it, and then check your work and identify whether you understand it or whether you might have questions. And again, you are always welcome to email me with questions. Okay, so calculating the partial derivative of this function with respect to x means taking the derivative of terms involving x. And as a reminder, any terms that do not contain x become 0 for the partial derivative with respect to x. Doing so gives ez dx is equal to 8x. Similarly, for the partial derivative with respect to y, we take the derivative of terms involving y, and any terms that do not include y become 0. So dz dy becomes 2y. So for the trace for y equals 1, we get z equals 4x squared plus 1. And we know that the derivative of this is 8x, which relates the partial derivative with respect to x. As for the trace for x equals 1, this gives us z is equal to 4 plus y squared, and this has a derivative of 2y, which again relates to what we had earlier. So we have now confirmed that partial derivatives represent two angles of looking at tangent lines, specifically parallel to the x-axis and parallel to the y-axis. However, again, we do not have a way of taking a tangent line that is diagonal. This slide here begins as a summary of what we have said. Partial derivative with respect to x, dz dx, is the slope of a tangent line parallel to the x-axis. dz dy, slope of a tangent line parallel to the y-axis. However, again, at the moment, we are not able to calculate a slope for any diagonal way of travel along the surface. And for that, we need directional derivatives, which we will go over shortly. Before we can take directional derivatives, we need a way to identify diagonal vectors on the plane. Similar to what we discussed Friday in class, that is prior to leaving for break, we can identify directions using an angle measured from the positive x-axis. And from trigonometry, any direction can be given for the x component, whatever distance we have from the origin times cosine, and along the y direction, whatever distance times sine. So we can represent what part of the direction what part of our diagonal direction is along x by cosine, and what part of our diagonal direction along y is by sine. This will then become useful in calculating directional derivatives. With this idea in mind, we come up with the directional derivative at an angle theta as being the partial derivative of the function with respect to x times cosine of whatever angle it is, plus the partial derivative of the function with respect to y times sine of whatever angle it is. We note the directional derivative with a capital D and whatever angle we have, in this case represented as theta. However, this will be replaced with whatever angle we insert. For example, below we will use theta is equal to pi over 3 for one of them, and theta is equal to 5 pi over 6 for another. So I suggest at this point you pause the recording and attempt to calculate this using the formula, and then check your work. So going ahead with this, for the first one, for d pi over 3, we have the partial derivative of the function z equals x cubed y minus 5x squared y squared with respect to x, which becomes 3x squared y minus 10xy squared, and that's multiplied by the cosine of our angle, so cosine of pi over 3. Then we have the partial derivative with respect to y of this function, which is x cubed times 1, which is just x cubed, minus 10x squared y, and that's multiplied by sine of pi over 3. Using trigonometry to calculate these, or using a calculator, gives 3x squared y minus 10xy squared times 0.5, as cosine of pi over 3 is equal to 0.5, plus x cubed minus 10xy times 0.866, as sine of pi over 3 is equal to 0.866. This can be simplified. However, in this case, this is an acceptable answer since simplification doesn't alter the result, and oftentimes we are trying to calculate this directional derivative at a certain point. Similarly, we can do the directional derivative for 5 pi over 6, which is pretty much the same as above, except for now we have cosine of 5 pi over 6 and sine of 5 pi over 6. By the way, there is a typo on the slide. Actually, never mind. That's a Z. Sorry, my vision is bad. Okay, so again, similarly, plugging into a calculator gives what we have right there. So that is it for this presentation. You are welcome to email me with questions. I hope you have gained something out of this presentation. Again, if you are watching this before Thanksgiving, have a happy Thanksgiving. If you're watching this afterwards, I look forward to seeing you in December. Thank you. Bye.